Hi, my name is Luc van Donkersgoed, and today I would like to talk to you about the CDK and the impact it has on serverless developers. But before we dive into the CDK, I would like to look a bit at the times before public cloud. So way back when we still had our own physical data centers and everybody was just putting in racks and still cutting UTP cables, there were generally two teams. You had the development team, which were responsible for software architecture, software development, unit testing, and if you're lucky, they would also write some documentation. Then you had the operations team, which were responsible for power supplies, networking, storage, the storage area network, operating systems, but also the applications, the libraries, and all the frameworks, and managing all of that for the applications that they hosted. And of course, they were responsible for monitoring, and if you're lucky, they would also write some documentation. So that got us to a situation where the development team might say, hey, it works on my machine, it works on my colleague's machine, so the application is good. But then they would hand over the application to the operations team, and they would deploy it to the production environment, and then it didn't work. And then that cost a lot of time to find out what the issues were, to fix those issues, and to actually get the application running in the production environment. And during this time, the application would be not available, it would be unavailable. So what they introduced were maintenance windows that could take hours, probably in the middle of the night, in which teams were deploying that application, seeing what worked, what didn't work, patching what didn't work, until the application was back online. And during that time, the users would not be able to use the application. So to reduce the amount of times that the users were impacted, they would reduce the amount of maintenance windows, sometimes to 4 times a year or even 2 times a year. So that meant that the application would get all these new features for months and months and months, and then all of those features and updates would be deployed at once. And that actually increased the chance of issues, because if you have hundreds of changes and you do a big deployment, it becomes really hard to pinpoint which of those issues actually cause trouble in the production environment. So to solve this, DevOps was invented, in which the development team was also responsible for the operations. The mantra is you build it, you run it. The way to achieve this is to test everything, to test every single change using unit testing, integration testing, deployment testing, stress testing, user acceptance testing, and all sorts of testing. But also the deployments would need to be automated. And the deployments would need to be tested. And if a deployment would fail, you would roll back the deployment. And this, if implemented right, makes it possible to do many small deployments, like every feature or every few features could be its own deployment. And public cloud plays a very important role in this, because now you can spin up new environments, spin up new services, and also tear them down again in minutes, instead of the old data centers where you had to buy the hardware, put it in a rack, and it would cost months to set up an actual new environment. And most importantly, in public cloud, you can have infrastructure as code. So now you can actually define your infrastructure like you would define your application in code, and you can apply all the DevOps principles on your infrastructure. So you can do versioning, you can do testing, you can do rollbacks. But most importantly, it makes it really easy to have multiple environments, because your application and your infrastructure is defined as code. So you have a template that defines your environment, and it becomes really easy to deploy that to production, and then deploy exactly the same environment to acceptance, to testing, to dev. And whenever you need a new environment, for example, a pre-production environment, you would just use that template, deploy it again in a new AWS account or whatever public cloud you're using, and it would be exactly the same. And that also allows you to do infrastructure changes in your acceptance environment, test it there, make sure that it works without any impact on your users, and then deploy exactly the same template to production. And in a way, serverless is the ultimate DevOps platform, because in serverless, everything is code, right? You have your file storage in S3, which are just APIs. You have your databases in DynamoDB, which are also just APIs. If you want to put a message onto an SQS queue, it's also just an API. And all of these APIs are available through SDKs in your favorite programming language. So you don't have any database protocol, you don't have to worry about the network, you don't have to worry about scaling, you don't have to know SQL, you just write code for everything. And this brings us to a new generation of engineers. These are the people who have never touched a rack-mounted server, who have never cut a UTP cable, and who might even not know what the UPS is. But these people know all about S3, they know all about Kinesis, they know all about CloudWatch, EventBridge, step functions, even if they don't know how to set up an SSH connection or how to extend a logical volume. And these people are great with Python, and they are great with Node, and they are great with Go. But to go fully cloud native, these people need to learn another language. And that's the language of their infrastructure. So in AWS, this might be CloudFormation, or it might be SAM or Terraform or another infrastructure as code language. And this language might actually not be as powerful as your core language. So the users might be using Python, and it has all these features like unit testing, like for loops, like conditions, and they might use CloudFormation for their infrastructure. And CloudFormation then requires hundreds of thousands of lines of code that has a lot of repetition, and it doesn't have loops, and unit testing becomes really difficult, and it just is not as easy or developer friendly as the core language these developers are used to. So let's just put those two platforms side by side. On the left side, we have the application. On the right side, we have the infrastructure. And the application is written in a code, in a language that is familiar to the developer, while the infrastructure might be an unfamiliar language. The application is fully featured, so you have loops and conditions and functions and classes. And the infrastructure code has limited features. The application might be object-oriented, it might also be procedural, but the infra probably is YAML or JSON or some other declarative language. The application is testable, while the infrastructure is hard to test. And most importantly, the application is compact and it's dry, right? You do not repeat yourself. While the infrastructure is very verbose, every resource is repeated and repeated and repeated again. So now all of this changed with the introduction of the CDK. So to tell you about the differences between old infrastructure, for example, CloudFormation, and the CDK, we will look at an example. But we will start by looking at an example application. So what we will be looking at is a Lambda function written in Python, which takes two objects in an S3 bucket, which have predefined object keys, and they check the contents of these objects for the word confidential. And if the word confidential is in there, they write some metadata back to S3. So in simple code, that might look like this. We have the Lambda handler, we have the key objects, we get the object from S3, we look at its contents, and if the content contains the word confidential, we write the object back to S3 with the metadata, with the checked add date, and the confidential, which is either true or false. And we do that for object A, and then we also do it for object B. It's very simple. But we don't really like this. We don't like the way this code was written. It's not very clean. So what's wrong with the code? Well, for example, we have a hard-coded bucket name. So that doesn't scale when your bucket changes, because now you have to update your application code. There are no comments, so it's pretty hard to read what is actually happening in the code. The object keys are hard coded, so if you have more object keys to check or the object keys change, that also makes it pretty difficult. And there's a lot of repetition because we have object A and object B, and they execute exactly the same steps, but they're here twice, right? So let's clean this up a bit and make this code a bit more modern. So this is exactly the same function. It does the same things. It has the same end result, but now it's improved a bit. So we have environment vars to set the S3 bucket. We have comments to indicate what the functions do. We have a loop that loops over all the object keys provided in the event. And then we have a function that checks the confidentiality of the object. And we have another function that updates the object metadata. And those two functions are used in the for loop. So now we have no repetition. The code is easier to read, it's cleaner, and it's easier to adopt to new changes. Now, to verify that this code works now, but also keeps on working into the future, we add some unit tests. So let's look at the first function. We have the check object confidentiality. We generate some input. This is the exact input generated by S3. And it has a body, and the body is, this body contains the word confidential. Now we have our unit test that takes this input, simulates the S3 situation, this S3 get object situation, and then we use the check object confidentiality with this input. And then we assert that this function get object is called once, and that it is called with the bucket and the key that we specified. And we also verify that the output equals true, because this body contains the word confidential, so the output should be true. And of course we do the same, but then with a body that doesn't contain the word confidential, and the output should be false. Then looking at the other method, the update object metadata, you provide a key and whether it's confidential or not. And then we also want to assert that the copy object function was called once, and that it was called with the parameters that we expect. So specific metadata that contains the word confidential is true. So now we've seen how we have Python code, and we can either have it very simply and plainly written without all the optimizations that you can do in code. And we've seen how we can optimize this code and make it a lot better. Now let's look at a comparable example in infrastructure. So again, we have an example use case. In this case, it's an API gateway, an HTTP API that has two routes. It has the getBooks route and it has getPaths. And those are backed by two Lambda functions. So first, let's store this information in CloudFormation. And CloudFormation is very powerful. I like CloudFormation a lot. It's very, well, you have versioning, you have rollbacks, you have drift detection, you have all these powerful features. But it is pretty hard to write and it's pretty hard to maintain. So let's take a look at what our API gateway looks like in CloudFormation. It starts pretty easy. We have the API gateway itself, and we have the default stage. That's 19 lines of code, and that's okay. But now let's add the two Lambda functions that we discussed, the getBooks and the getPaths. First, the getBooks function. It's the Lambda function itself. It points to an asset bucket and it points to an S3 key. And it has a service role. That's the IAM role that specifies what this function can do. So that's a reference to another resource in this CloudFormation template, another 30 lines of code, which says what this function can do, what it is allowed to do in its AWS environment. And in this case, we just have the managed policy, AWS Lambda basic execution role, which makes sure that it can write to CloudWatch. But with the function and the service role, we have the function and the API gateway, but we don't yet have a connection between API gateway and the Lambda function itself. So to add that, we first add a route. which is get/books, and that points to another resource, which is the HTTP API getBooks integration. So let's take a look at the integration, and this is that integration. This points to the specific function and links the getBooks route to the getBooks function. So now we're almost done. The last thing that we need is to give API Gateway an actual permission to run the Lambda function, or actually, technically, it's giving the Lambda function the permission to be called from API Gateway. And now we've set up everything that we need. So you think we're done, right? But we're not, because we still have to do exactly the same for get_pets, and that's another 120 lines of code. So quick tally, we have 12 resources for our API Gateway with 2 routes. It's 250 lines of JSON. There's a lot of repetition. There's no comments, there's no test, there's no loops, and there's no function. So let me ask you, does this make the born in the cloud engineer happy? Is this easy to learn? Is it appealing? Or to channel our inner Marie Kondo, does this spark joy? And of course the answer is no. So there have been a lot of alternatives in the past, and they all solve a part of the puzzle, but still it's not really a cloud native way or a born in the cloud engineer natural way to write infrastructure as code. You still have to learn Terraform, or you still have to learn CloudFormation, or any of these other languages which might be limited in their feature set or not. So now let's look at the CDK. And first let's look at a simple example that generates exactly the same CloudFormation that we just saw, but now defined in Python. So we have our CDK generation stack here. And first, in one single line, we define the API gateway, and this automatically generates the default stage as well. And then we have the getBooks function, which points to the application source and sets some variables like which Python version it runs. We create a books integration that points to the books function, and then we add a route to the HTTP gateway that points to that integration. And then we do the same thing for the get_pets. So this does exactly the same as the CloudFormation template that we just went through. So we went from 250 lines of code to 50 lines of code, which is already a great improvement. But we aren't there yet. So in this Python stack, we still have no comments, and there's a lot of repetition, which is what we saw in the Python application earlier as well. So how do we solve this in CDK? Well, first we create an L3 construct, which is also called a pattern, that contains the common resources that we're using for our route. So in this case, we create the Lambda function, and we create the API integration, and we add a route to the HTTP API, and we add some comments as well. And now we can use this pattern to create all of those resources for our specific endpoints. So we have the construct ID getBooks, and we provide the specific parameters for this endpoint. And then we also provide the same parameters for the get_pets endpoint. And again, we don't have the repetition that we saw before. So this is a lot cleaner, and this code actually starts to look a lot like the application code that we wrote earlier, and that we as developers are used to. So about those serverless developers, right? Just to do a quick recap. They write their code in Python. They had to write their infrastructure code in a language like JSON or YAML or Terraform. But now with the CDK, they can use the same patterns and the same logic that they were used to in their own code, and apply that to their infrastructure. But now that we have a fully featured language to generate our infrastructure, there are a lot of new things that we can do as well. So let's take a look at the kinds of things that we can do. Let's say we have an application and an infrastructure for a SaaS environment, right? Software as a service. You have many tenants that use your application and they all share your environment. But in this infrastructure, every tenant, so every user of your SaaS application, gets their own S3 bucket. And to configure those S3 buckets, we want to have a configuration file that defines which users or which tenants are in our application. And this configuration file might be managed by an entirely different team, or it might be managed by the sales department, or it might be auto-generated. We don't know, and we don't control this configuration file. We just parse it. Now, in this configuration file, it says what the name of the tenant. It says whether the bucket should be public and whether versioning should be enabled on that bucket. Now, let's look at the CDK code and see how we can use this. What we can do is open the tenants file, and that generates a tenants config. That generates a list of tenants which we can loop over. And then for every tenant that we find, we first normalize the name, and then we create another pattern, which is the tenant bucket for every user. So let's take a look at what that normalized tenant name function does. It's actually pretty simple. We take the tenant name as provided in the configuration name. We only take the letters and numbers, so the alphanumeric characters from the name. We remove everything else, and then we convert it to lowercase. And the reason we do this is that we're going to use this name in a number of places, but specifically the S3 bucket name. And the S3 bucket name has some restrictions on what you can use. So we don't want any weird characters. We want to control the capitalization. And to do that, we use this normalized tenant name. So let's look at the stack generation code again. We take this name, and for example, here we see that the normalized name is then capitalized and used in the construct ID for every tenant. Now let's look at the L3 pattern itself. It does a few things. First, it checks if the name is actually provided, and it raises an error if it isn't. Then it normalizes that name again. Then it takes the versioning enabled parameter, which is optional. If it's provided, it stores it in the bucket versioned variable. If it's not provided, it defaults to false. And the same goes for the bucket public variable. And then it creates an S3 bucket using, again, the normalized name. So this is where the S3 restrictions come in. And it sets a versioned and public read access variables. It also sets the block public access variables to the inverse of the bucket public variable. So if the bucket should be public, then public read access is set to true. And then the block public ACLs are set to false, so that is actually allowed to be true. And the other way around, if public read access is set to false, so the bucket should not be public, then all of these block rules are set to true. Now, if we run this code, the CDK code, so run the CDK synthesize, it generates the following CloudFormation template. And you can see here the PostNL bucket pattern resource. And as you can see, the name has been normalized to completely lowercase and a uppercase p. And the bucket name is completely lowercase. Now this bucket was configured to be public, so we see that the block rules are all set to false, and it also automatically generates a bucket policy that makes this bucket actually public. If we look at the next one, we see the Sentia bucket. Again, you see the normalization and you don't see the policy, but you do see that all the block public rules are set to true. Then we see the Nederlandse Spoorwegen, which is the Dutch railway company. And we see that the original name had a space in it, but the space has been removed and everything has been converted to lowercase as well. And the last company that we had a placeholder name, which had an underscore in it. And as you can see, the underscore has been removed as well. Now we get to a situation where this configuration file is managed by somebody else, and that somebody else might choose to fill in a company name that doesn't match our requirements at all. So for example, they might put an emoji in it, or they might go completely mixed case and so on. But we want to be sure that whatever they input, we generate a bucket name that actually works. And the way to confirm that is to write a unit test that takes those different inputs and validates that the output is actually what we expect. So let's take a look at our L3 construct again and see what it is that we actually need to test, right? So we see that we expect a value error if the name is not provided. That's something to test. We see that the name is normalized and used here, so we need to check different inputs and different outputs. And we see that the bucket versions and the bucket public variables have defaults if they're not provided, and they should take the value from the config file if they are provided. So those are things that we want to cover in unit tests. So the first thing to test is the missing name. And I used the AAA principle on my unit test, so I always arrange and then act, then assert. In this case, there's nothing to arrange. We just want to create a new tenant bucket, provide empty parameters, and verify that this raises a value error, and that the value error contains the text missing tenant name. Then we want to test a bucket with minimal parameters, so it uses the default settings for versioned and public bucket, but we do provide a name. And what we want to verify is that the version setting is indeed set to false, that the public read access setting is also set to false, and that the block public access values are all set to true. Now we do the same, but then we set the versioning to true, and we want to verify that the value for versioned is indeed set to true. And we do the same for public bucket. But of course, the most important thing to test is the name input. So here we have one with a mixed case. We have test tenant with all these capitals in it. And we want to verify that the ID and the bucket name are completely lowercase. Then we have one with symbols. So we have this really strange customer name or tenant name. And we just want to verify that all we have left is test102 test. And that is what the bucket is actually created with. Then we have a name with spaces in it, and we have test1, test2, test3, and we want to verify that all the spaces have been removed as well. So that's what we have this unit test for. Now, if we run this unit test suite, what we see is that it first tests the application. So the check object confidentiality true and false that we saw in the beginning of the application, or sorry, in the beginning of the presentation. And then it tests all the unit tests, or it runs all the unit tests that we just specified in the previous slides. So what you see here, and what this screenshot is really an example of, is that the application code and the infrastructure code are now one and the same thing, the same module. And that really makes sense from a serverless developer's perspective, because you're writing code and your code might impact your infrastructure, but you're constantly switching between the two. So for example, you create a new Lambda function, that's the infrastructure, and then you create the actual code for that Lambda function, that's your application. But it makes sense to have that in the same environment and to have a single test suite and a single language to write both your infrastructure and your application in. So that leads me to the conclusion, right? In the beginning, we saw how we can have a Python application and the things that we can do to optimize that code. We removed repetition, we added some comments, and we added some unit tests. And now in the previous slides, we can see that we can apply the same principles to our infrastructure, right? We also removed repetition, we added comments, and we added unit tests. And you can do this in a common language, the language that you're used to. So in my example, my application code was Python and the CDK was also Python. But CDK also supports TypeScript, JavaScript, Java, C#, and currently in developer preview also supports Go. So if you're writing your code in any one of those languages, you can now write your infrastructure in the same language using the same tools, the same way of unit testing, the same optimizations that you're used to in your application code. And I believe this will be an enormous step forward for serverless engineers, for born in the cloud engineers, who are used to writing code and to having APIs and SDKs for everything, and now have a very low barrier to writing infrastructure as well, infrastructure code, which makes it easier to apply DevOps practices and makes it easier for these born in the cloud engineers to apply the best practices across their entire code base. And that's it for today. Thank you for watching, and if you have any questions or remarks, reach out to me on Twitter.